Hello everyone, so welcome to our new lectures. So in these lectures, I will introduce some new materials of our hypothesis. So here on our previous lectures, we always works on one populations. So we will have one populations and it follows a normal distribution, and then we will select one sample from our population, and then we will use the hypothesis test to check about the mean of some assumptions. We based on the variance is known or unknown, we will do this. However, in these lectures, we will work on the statistical inference for two populations. So the topic is about inference on the difference in mean of two normal distribution. And here we more focus on the variances unknown. But at the first part, of course, I will give a brief introduction about what should we do if we know the variance. So here, if we have two populations and both of them are normal distributions, so what we will have two means. So here for these two means, we will denote it by mu1 and mu2. And based on each of these populations, we will select one sample. And then for these two populations, we denote this sample size as N1 and N2 responding to our number of the populations. And then for our hypothesis test about the mean, generally we know for hypothesis test, we will have a null hypothesis, which is denoted by an H0. And this is always an equation. And sometimes we will denote this by mu equal mu0, and here mu0 is any constant. However, for here, what we are interested because we interested in the difference between two means, so what we will write for our null hypothesis, this will write as a mu1 equal mu2, or mu1 not equal mu2. So here, this is look like this equation. So based on our null hypothesis, we will have our alternative hypothesis. So for this one, still we will have three types of our alternative hypothesis H1. The first one is our two-sides test. So this is a inequation. So it's a mu1 not equal mu2. And then the second and third type is one-side test. So we always have the second one is use a larger, one thing is larger than another thing, and the third one is mu1 is smaller than mu2. So if we look at this equation, maybe you think this is not exactly same with our original or our previous lectures. Because for our previous lecture, what we always say mu is equal a number, or larger or smaller than number, not equal a number. But here what we have, mu1, mu2, both of them is some parameters of our populations. So what we can do is we can rewrite this setting of our hypothesis to this second equation here. So we can just move the mu2 from the right side of our sample to the left side. So for the null hypothesis, we will have mu1 minus mu2 equals 0. So now we have a number on the right side of our equation. And similarly, we can write the equation for our alternative hypothesis as this follows. So then what we want to do next. So for this one, we should decide what is our test statistics, right? So previous, we already talked about the hypothesis about mean for one population. So because for mean, we always use X bar, the sample mean, to create our statistic. So here, the idea is similar. The only difference is now we have two mean. So we will have two sample mean. So we denote one by X bar 1, the other by X bar 2. And for these two sample mean, by the information of our original population and the sample size N1 and 2, we know the X bar 1 follows a normal distribution. with the mean is still same with our population as mu1, and then the variance is sigma 1 square over our divided by our n1. So this is based on our property of the variance for the linear function. And then similar for our sample mean of the second population, is about mean is mu2 and the variance is sigma 2 square divided by n2. So now what we have is we already have this the distribution of these two sample mean. And then if we want to check the difference between this sample mean, what we know if we have x bar 1 minus our x bar 2, this is still a normal distribution. And the mean is mu1 minus mu2, and the variance is the sum of the two variance of these two distributions. So it's a sigma 1 square divided by n1 plus the sigma 2 square divided by n2. So now this is the distribution of the difference between these two sample mean. So based on this information, what we can do is we can start our z-test, right? Because z-test is always with the normal distribution, and t-test is for the t-distribution. So for here, assume if we know these two variance value, we know the value of sigma 1 and we know the value of sigma 2, then we will have this equation. So this we have the z0 is equal to this complicated equation. So the numerator is still about the sample mean minus our true value of our mean. But here we work on the two populations. So that's why the first parenthesis we have the x bar 1 minus x bar 2. And the second is about mu1 minus mu2. And then for the denominator, it's still about the standard deviation. And now, because our original distribution is sigma 1 squared divided by n1 plus sigma 2 squared divided by n2, so now we will have the square root of the whole of the variance. So we know this z0 is our standard normal distribution. So this, if we know this is a standard normal distribution, then about to compute about the z-test or compute about the confidence interval, we can follows exactly what we talked about before about how to do this with some calculator and also the table of the standard normal distribution. So here I will skip this part because we already have several examples about that steps. So now what I want to work here is, in case if we don't know the exactly value of our variance sigma 1 and sigma 2, so what should we do? So here we need to divide this to several cases. The first one is we will assume the variance of these two populations is same. So that means we can rewrite our sigma 1 and sigma 2 as this equation. So sigma 1 square equals sigma 2 square equals sigma square. So now sigma is some value we don't know, but we just denote this as sigma. So then later we will always use sigma to denote it, to create our equations. So now what we should do when we don't know the sigma. So previously when we talk about how we can do the hypothesis test or how we can find the confidence intervals when we don't know the variance of one normal distribution population, we always use the point estimator of our population variance to substitute the sigma in our formula. So what we should do here is same. We also use the point estimator of our population variance to replace the sigma in our formula. The only thing we need to do here is, because sigma 1 and sigma 2 is same in our case 1, so we will use the pooled sample variance which means this is weighted by the sample size to create the point estimator of our population variance. So here maybe you will ask me why we don't, because we know this sigma 1 is equal sigma 2, why we don't only use like the sample variance of the first one to estimate our sigma here, or maybe just use the sample variance of the second one to estimate our sigma. So the reason is, please remember in statistics, the data is very is valuable. It contains the information, valuable information. So we will always try our best to use all of the data. So if we only use the sample variance of the first one, it means we will ignore all the information from the second sample. In the opposite way, it's the same. We ignore all the information contained in the first sample. So based on we don't want to ignore any valuable information here, right? So a better way is we use a pooled sample variance weighted by their sample size to create our point estimator. So this here, of course, I give the formula for this, our S square P. So this is our degree of freedom for our first sample divided by the degree of freedom for the two sample, right? So that's why it's n1 minus 1 divided by n1 plus n2 minus 2. And this is our weight for the first sample variance as 1 square. And then similar for the second one is use the degree of freedom for the second sample divided by the degree of freedom for the whole sample, and then times our second sample variance. And of course we can, this is a two-part, and of course we can rewrite this as a one equation. So this is read as this equation. So here for this one, because this is the first time we use this pooled sample variance, so I want to talk a little more about this, our S square P. So in fact, actually we can know this SP square is an unbiased estimator of our sigma square. So I write down this here as a remark. So I always use the red color for remark. So why this is an unbiased estimator? So we already taught what is an unbiased estimator. It means if we have the expectation of our estimator, this expectation of S square P is equal our original value, right? Equal the sigma square. Then we can say this estimator is an unbiased estimator. So in fact, let me explain this by one equation here. So this is, so here I use this green color to write our explanation. So here, what we can do is, of course, we know there is a linear property of our mean, right? So that's why when I denoted the n1 minus 1 divided by n1 plus n2 minus 2 as W, then we can use the linearity of our mean to rewrite the expectation, the mean of our S square P as this equation. So then by some calculation, because we know here the sample variance is an unbiased estimator of our population variance, right? So that's why the mean of our S1 square, E S1 square is equal sigma square. And this is same for our S2 square. So that's why by some calculation, we know the ES square P is equal our sigma square. So that's why we can conclude this SP square is an unbiased estimator of our sigma square here. So now we already know we have this estimator of our sigma square, our population variance. So next what we can do is when we calculate our test statistics, what we will have based on this situation, when the population variance is unknown, we can create a test statistic, and also this statistic is a T-distribution. So this is very similar to our previous lectures. So this is a T-distribution with a degree of freedom as n1 plus n2 minus 2. So here, of course, this T-test is still, this test statistic is still our the difference of the sample mean minus the difference of our population mean, and then divided by the standard deviation. But here what we do is we will use our point estimator as p square to replace our sigma square, right? So here this is what we have. So because we already know this t-test, this statistic t0 is a t-distribution with n1 plus n2 minus 2 degree of freedom. So then what we can do is for the hypothesis test, we can, exactly same with our previous lectures. We still do the test, but the only thing is now if we use the T sub alpha or sub alpha over 2, what we need to careful is we need to careful about our degree of freedom. So that's why we use the T alpha over 2 comma n1 plus n2 minus 2 for our two sides test. And then for the one side test, we will use T alpha comma n1 plus n2 minus 2. So this is what we have for the hypothesis test. And then of course, here what we talk about is statistical inference, right? So this have two parts. One is about our hypothesis test, and the other one is about the estimation. So here about the estimation, what we will use is, I want to talk about the confidence interval here. So let's we also talk about the confidence interval. So here I still use the C dot I dot to write the confidence interval for short. So here, of course, for the confidence interval, what we will do is first we should give a confidence level, right? So this is generally denoted by alpha. So here, what we want is if we give about a confidence level about the alpha, then we want to know what is a confidence interval. So in other words, is the estimation of the difference between our mu1 and mu2 has like maybe 95% to fail in our confidence interval. So this is the meaning of our confidence interval, right? And then let me write this formula for our confidence interval. So this is for our 101 minus alpha percentage confidence level. The confidence interval is denoted by this equation. So the left inner point is our difference of the sample mean minus our critical minus our here this one. So this is T alpha over 2. T alpha over 2 n1 plus n2 minus 2 times our this standard deviation we have for the pooled sample. And also we similarly will have the right inner point. So here is similar to our previous lectures. We still code about this equation, this complete part. This is still our margin of error. So this is about the confidence interval for this case. So please remember now what we have. We always say we will have our sigma 1 and sigma 2 equal each other. So that's why in this equation we use the pooled sample variance to estimate our sigma. And then the next thing, I want to give this example. So here in this example, we work on about the confidence interval. So here we have two machines produce the steel rods, and so here for their diameters, this is follows a normal distribution. So now we select one sample from the first machine with 15 rods, and then what we have the information about this first sample is the sample mean x bar 1 is equal 8.73, and then the sample variance is equal 0.35. And also we will select another sample from the second machine. So here we have 17 as our second sample size. With this sample mean x bar 2 is equal 8.68, and also the sample variance x2 square is equal 0.4. So now the question is how we can find the confidence interval for the 95%. And please remember here we assume sigma 1 square is equal our sigma 2 square. So to finish this question, what we can do is we can use our formula to get about our left endpoint and right endpoint of our confidence interval. But before that, the first thing we need to do is we need to compute what is our pooled sample variance, our S square P. So here we need to plug in all the information we know in the formula of our S square P. So here, because N1 is equal 15, N2 equal 17, and also we have S1 square equal 0.3, S2 square equal 0.4. So based on this equation, we can use a calculator to help us compute this value. So the value of this equation is 0.37666. Until we just say 7 at round to this number. So then after we have this value of our SP square, the next thing is we just plug in this one to our equation, right? So because here for this confidence interval, what we do is we can just write the critical value, right? So our critical value, the formula for our critical value is look like this. So here, except this SP square, the other thing we need is our alpha. So here, because the original we have this is a confidence of the 95%, and we also know here for our alpha, this is equal 1 minus our 95%, right? So that's why for our alpha, this will equal 0.05. And so that's why our alpha over 2 will become a 0.025. So here, now we can plug in all of the information we have into the formula of our critical value as this equation. So here, because we have the x bar 1 is equal 8.73 and x bar 2 is equal 8.68. So now we can plug in all the information we have into this equation. And it's a little looks complicated. And so before we use our calculator to compute this equation, one more thing we need to do is we need to use a table of our T-distribution. So here, this table we use for the T-distribution, we need to find the value of our T sub 0.025, comma, the degree of freedom. So here, the degree of freedom is 14 plus 17 minus 2, so it's equal 30. So based on the information we have from the T table, and then use our calculator, we can compute the result of this equation is like this. So 0.05 plus or minus 0.444. So because this is our critical value, so we know the left endpoint is 0.05 minus 0.444, and then the right endpoint of our confidence interval is 0.05 plus 0.444. So then we will have our conclusion. Our confidence interval is, this is between negative 0.394 and positive 0.494. So this is our answer for the confidence interval. So now what we done is we already talked about if we know the variance, then how we can do the hypothesis test. And we know if we don't know the variance, sigma 1 and sigma 2, then here we work on the first case. If we assume sigma 1 equals sigma 2, we denote this by sigma. So we can use the pooled sample variance to estimate this one. So then we can use the Tdistribution, Ttest, to do the hypothesis test. And then we can also create our confidence interval by this Tdistribution and Ttest statistics. So the next thing is, let us move to the other case. So this is if we can't have the equation between sigma 1 and sigma 2. So then what should we do? So we will use the first sample variance to replace our sigma 1, and then use the second subvariance the S2 square to replace our sigma 2 square. So then what we will have the test statistic is right like. So then we can also create our Ttest test statistics, and this is the formula of our test statistics. It looks very similar. So here to differentiate it, I denote this as T0 star. So you can see, except we use S1 square and S2 square to substitute our sigma 1 square and sigma 2 square. So the test statistics looks very similar for our previous case. So of course this is still a Tdistribution with a degree of freedom. Here I denote this by V. So this actually the hard part of this one is about what is a degree of freedom. So in fact this degree of freedom is a kind of complicated equation. So let me write down it here. So here we can know the numerator is a square of a sum of S1 square over N1 and S2 square over N2. And then the denominator is a sum between two parts. The first one is the numerator is square of S1 square over N1, and this is divided by N1 minus 1. So this is a degree of freedom for our first sample. And then the second part is a numerator is square of S2 square divided by N2, and then this square is divided by the degree of freedom of our second sample. So of course, if we compute this one, this may be a decimal number or is an integer number. However, we know the degree of freedom for a Tdistribution is always an integer. So what we should do is, of course, here we should round our number. So what we will do is we will round down this to some interested number. So here this is based on the T table we use. So you can just round down this to the number you can find in our T table, because I think you already use our T table a lot, right? So you can find for our T table, the degree of freedom is not exactly 1, 2, 3, 4 until maybe 100 or even larger number. We in the T table is only select some of the degree of freedom. And of course, in the future, if you use some other T table, is we'll also have a different select of the degree of freedom. So this is based on the T table you use. So we will always round down this number to the close integer number we have in our T table. So this is what we have for the T-test. So of course, after we have this test statistics, and we know this is a T-distribution, and we know what is our degree of freedom. So if we want to do the test of this hypothesis test of this one, so we will still, for the two-side test, we use the T alpha over 2 with this V as our degree of freedom. And then for the one-side test, we use T alpha and with this V as our degree of freedom. So this is, here I won't repeat this again in this part. And then before the end of the new materials, let me give about the formula for our confidence interval, right? So here in this case, our confidence interval looks like this. So here, if we compare this with our previous case, case 1, everything is similar, just instead of use SP square, what we use here is S1 and S2. And also the other change is instead of use the N1 plus N2 minus 2 as our degree of freedom, so here we use a very complicated equation V as our degree of freedom. So here this is a formula for this part. So before the end of this video, let me give a quick example about how we can use this part to solve some problems. So this is test the claim that the machines produce the rods with different mean diameters with our alpha is equal 0.05 and sigma 1 is not equal to sigma 2 in the previous setting. So previous we already have one example, right, about the two machine product about the rods, and then we also have about the sample mean and sample variance, the x1 bar, x2 bar, and s1 and s2 in the previous question. So now in this one, what we should do is, here in this one, we will work on the hypothesis test. So here they ask us about test the claim that the machine will produce a mean diameter is not equal. So although the question is still, this question is interested in the mean is different, but when we create our hypothesis test, we always use the null hypothesis as an equation. So what this means? This means when we write down when we create our hypothesis test, so here when we write down the H0, this is always denoted by mu1 equal mu2. So here the question is asked about the difference of the mean of the diameters, right? So this tells us our H1. H1 now should be a two-side test. So that means our H1 as mu1 not equal mu2. So this is what we have for this hypothesis for this test. And then the next thing is, of course, what we should do is, for the hypothesis test, we always say we will assume our null hypothesis is correct. And then we will compute a test statistic and see is there some weird thing happen. So if there is something weird happen, then we will reject our null hypothesis. Otherwise, we will accept or we fail to reject it. So here, what is our test statistic? We use the T-test, right? So this is our T star. The equation is like this. So now we need to plug in the value of our x1 bar, x2 bar, and S1, S2, N1, N2 in our equation. So we will have this equation is become, so here because we assume the H0 is true, right? So that's why mu1 minus mu2 is equal 0. And then we plug in all the value here, and by calculator we'll have the answer of this one is 0.231. So this is a value of our t-test. And then what the next thing is, now we need to compare this with our use this one to compare this with our critical value, right? So what is our critical value? Our critical value is a T alpha over 2 and comma the degree of freedom. So here, because this is a two-sides test, so that's why we use T alpha over 2. And the previous we already know the degree of freedom is very complicated, right? So instead of just use the table of T, let's ask to compute the degree of freedom V here. So I already write down the formula for our V degree of freedom here. So then we just plug in all of the values we have for this S1, S2, and N1, N2. So when we plug in all of the values here, so what the number we have, we need to use a calculator to compute this. So the final one is about the 29.88. So here the next thing is, of course, the degree of freedom should be an integer, right? So we need to round this number. And we say we always round down this number. And in our table of T-table, we have the degree of freedom, the information about degree of freedom equal 29. So that's why here we will get the round down of our degree of freedom V can equal 29. So this is our degree of freedom. And then similar with the previous example, right? So now our alpha over 2 is still equal 0.025. And now we know our degree of freedom is 29. So that means our critical value is T sub 0.025, comma, and 29. So this is the number we need to find for our critical value. So then by the table we use, the T-table, we will get this number is equal 2.045. So this is our critical value. So now we already have this critical value. So what should we do? The next thing is we need to compute compare of our T-test statistic value with our critical value. And then we say if our value of the test statistic is smaller than our critical value, then we will fail to reject our null hypothesis H0. Opposite one, if our critical value is smaller, then we can reject our H0. So here in this case, we have one is a 0.231, the other is a 2.045. So of course we will have our critical value is larger. So that's why we will get we fail to reject our null hypothesis. So this is about the example of how we can use the formula to do the hypothesis test. So then if you look at the result of our second example and the first example, so when we do the confidence interval of our difference between mu1 and mu2, we can see in fact this confidence interval is from a negative left endpoint and a positive right endpoint. So that means 0 is already in our confidence interval. So actually, because we have this question, we all work on the 95%, right, as our confidence level here. And what we can conclude, in fact, is because 0 is already in our confidence interval. So that means a claim or the hypothesis of mu1 equal mu2, or in other words, mu1 minus mu2 equals 0, is already can be inference or implied by this confidence interval. So this is the last thing I want to write it here. So this is a remark. So if 0 is not in our confidence interval, then we will reject our null hypothesis H0. And of course, this is only work when our original, the null hypothesis is mu1 equal mu2, and the alternative hypothesis H1 is mu1 not equal mu2. And of course, for this hypothesis test and for the confidence interval, we need work on the same accuracy level, right? So that means we will have also one is for the confidence level alpha, and the other is work on the significant level alpha. It should be same. So this is the end of our videos. So we will continue on the statistic questions in our next lectures. So thank you for your watch this. See you in my next video.